Welcome back, everyone. So for a change of pace, we're going to talk about HDF Server now, which is a project I've been working on for years. So my background, I guess I'm a senior architect at HDF Group. I started HDF Group in 2014. My focus has been on enabling HDF for the cloud. Prior to that, I was a dev manager at Amazon, and even before that, I worked at Intel, and that's where I first met Mike and Elena and got to know about HDF5. So we're going to talk about the motivation for HDF as a service, the architecture, client libraries and tools, a case study, a bit about Jupyter Lab, and demo, if I have time to fit all that in. So HDF as a service. So in the Lena's presentation, she talked about the library, right? So library exists as a thing applications link to, and they typically are writing to local files. When you have HDF as a service, the service is off somewhere else, right? And you're communicating it through an API, in this case, a RESTful API. And the benefits are that you're language independent, right? It doesn't matter you're C or Java or Python, and that you have this uniform resources, right? So a data set can just be a URI and says, here's my data set, or here's my selection of a data set. So we know how it's so convenient, like on the web, to send bookmarks, right, links to other things. We can do the same thing now for HDF5, right? You can have a link to a particular attribute or a particular data set or region. So history is started in 2014, even before I joined the HDF Group. One of our colleagues, Geert Heber, wrote a white paper, RESTful HDF5. I started in 2015, and we initially created this prototype called H5Serve, and some people in this room are still using that or derivatives of that. And then in 2017, NASA funded us to create a scalable version of the server, which we call the Highly Scalable Data Server, or HSDS. And in 2019, we have a commercialized version called KEDA. So you'll hear HSDS or KEDA, but they're basically the same thing. So characteristics of a REST API. Okay, you separate the concerns of the client and the server. The server maintains the resources and their state, and the client can learn about the state by sending REST requests to the server. It's stateless, so the server doesn't maintain any client state. Okay, so if you, in the world of the web, right, your clients may come and go. If the server had to keep some kind of resource for every client who may have connected at some time or another, that can get very expensive. And also, if you have client state on the server, it makes it hard to do things like round-robin requests to different machines, right, that are maintaining the server. It's cacheable, so clients can cache their responses. It's uniform, meaning that it uses the standard HTTP semantics of using the get, put, post, delete request, and following the conventions of that, right? So in HTTP world, gets are idempotent. Because on the internet, you're sending requests out and they get lost. You want to repeat that. So, clients understand what is, servers should do in those cases. So first, let me talk about H5Serve a bit and kind of go back to this evolution of how we got here. So the primary intent of H5Serve was to demonstrate the REST API. And it's a relatively simple implementation, right? We had the client would talk through REST to H5Serve, and on the machine running the server, there'd be an HDF5 library, and the H5Serve would talk to that library, and the library would write files on disk. And that worked pretty well as far as it went, but there are certain limitations, right? Each request to H5Serve was handled sequentially. So if you had a bunch of clients talking to H5Serve, they would have to wait in the queue for the previous requests to be handled. So it definitely wasn't a scalable system. So addressing this with HSDS, well, our ambitious goals were to handle any request load, any number of clients, any number of files, to support multiple reader, multiple writer. So Lane was talking about Swimmer, single writer, multiple reader. In HSDS, we want to support any number of clients reading and writing the same data at the same time. And these goals led to this idea of using object storage rather than POSIX. POSIX has some limitations when it comes to really scalable data services. To use a container-based approach, and I'll talk about how containers work within the framework of HSDS in a bit. And rather, this is a little contentious, but rather than use HF5 library as a totally clean implementation of all the HF5 features, right? So this is developed in Python, and it's independent of the library itself. And we call this HSDS. So a bit about object storage. So object storage in a way is a simpler system than POSIX, right? Because you don't have the POSIX semantics, you don't have directories, all you have are keys and objects. And for organizations that are creating large storage systems, it's usually generally cheaper to build and scale and maintain than POSIX-based systems. And in the cloud, it's predominant, I think, for any kind of large data collections. On Amazon, we have S3, Azure has blob storage, Google has Google Cloud Storage. And then for non-cloud, there are various storage systems, Ceph, OpenStack Swift, and OpenIO, where we have some of our friends from OpenIO here today. So now we try to think, okay, how do we marry object storage with HDF? Well, one, it's not compatible with H5 library, right? So HF5 library assumes that there's this POSIX storage system behind it. Compared to Disk.io, the latency talking to an object storage service is quite high. So imagine we have a request coming from a client that's hitting the server. The server needs to go to another service that's doing the object storage system. So we have this jump, and that builds up latency. Another challenge is it's not always read-write consistent, right? So for example, S3, if you write 42 to an object and then you come back and read it, you make it 42, you make it the previous value that was stored there. And another challenge is that when you write an object, you have to write the entire object. You can't do partial updates like you do in a POSIX file. And finally, you can get really high throughput, but it's hard to do high throughput with a single thread, right? You need either multi-threading or asynchronous updates. So that's how we got to not using the H5 library in HSDS, but creating our own new implementation. So what's the big idea here? Is rather than in the HF5 file, you have a file, and inside the file you have objects like groups and data sets and chunks. In HSDS, we store those objects as separate storage objects. So each HF5 group or data set becomes a JSON object in the storage system. Each chunk in each data set becomes its own object. So this means we can cap the maximum size of any object. So if you aim for your chunks between, say, 2 and 4 megabytes, then the largest object you'd have in the storage system would be 2 and 4 megabytes, even though the overall collection may be many terabytes. And how this works is here I have a diagram of a data set, and I've drawn these heavy boundaries represent chunks. And each of those chunks gets stored in the storage system as an object. Oops. Okay, so now how does this work with the service? So I mentioned containers. And we implement HSDS as a set of containers, and there are two types of containers. There are blue containers, which are the service nodes. They handle requests that are coming from the client, possibly through a load balancer. And service nodes do things like validate the requests, authenticate the user, make sure the user is authorized to do the given operation. And then the service node maps to one or more of these data nodes. And how this works is that in the storage system, you have these maybe many millions of objects, and there's this virtual partitioning of the storage system. And each data node owns one partition. Okay, so you can have one data node, or you could have 100 data nodes, but either way, you've segmented the storage space into these partitions, and each data node owns its partition. And this means that a given data node is the master of its set of objects. So when I mentioned this problem of non-consistent write and reads. Because the data node is only a person who's reading and writing those objects, it always understands the current state of that object. Okay. Now, we have these, in this example, we have 4 data nodes. When I have a request that comes in, say here, client wants to read this yellow rectangle. It happens to overlap 6 chunks. And going here, when that request comes to a service node, it can deterministically, so service node can go here and say, okay, I need to read 6 chunks, and there'll be probably all 4 of these data nodes will be involved. And it, in parallel, sends a request to each of these data nodes to do their read or write. And this means that each data node can be reading and writing to the object storage system simultaneously. So getting the data simultaneously, uncompressing and segmenting the data, and so on. Once all those requests are complete, the service node assembles a response and returns it back to the client. So this provides a couple things. One is scalability. If you can increase the number of data nodes, you increase the amount of possible parallelism you can get with the system. The other thing is it gives us this ability to have the multiple reader, multiple writer. Because say we have multiple writers or writing to one data set, if those writes are non-overlapping in the chunk space, different data nodes can be processing those in parallel. If they are overlapping in the chunk space, then there'll be a last writer wins kind of setup where the same data node will have to handle the first write to that chunk and then the second write to that chunk. But the update will be consistent, meaning that it won't be ambiguous in terms of what gets written to the object. All right. Okay, so that's the service. And now let's think about clients. Okay, let's what it is. So you could have, say, a web application that is going to create a AJAX type of UI. And that application could just use the REST API directly talking to the service. And that's really cool. Or you could have, say, a Python application that was written to use H5Py. I probably don't want to rewrite that application using REST API, but conveniently, we have a package called H5PyD, which stands for H5Py distributed, and it has the same API as H5Py. Except now, instead of talking to the library, it's talking to the REST API, and the REST API is talking to the server. So this lets you take existing applications and pretty much use those without any changes with the server. If you have a C or Fortran application, you can use the library, and here we're injecting a vol. So Lena talked about the vol architecture. The REST file does the same kind of thing. It takes HDF5 library API calls and converts those to REST requests, and then go to the server and come back to the client. So again, you can have existing C and Fortran applications work without change, but now their context is going from the library and local files to connecting through the server. All right. Oh, and finally, command line tools. I'll show these a bit later. These are utilities to do things like upload a traditional HTML file to the server, or download for the server to a traditional HTML file to list your content. In the POSIX world, we assume you'll have commands like ls, or chmod to understand the state of files. That's not the case in the object storage world, and there are utilities that will say list the files in a certain path. Okay, and then finally for Kita, we took the open source HSDS project and we added some special hooks for customers who are looking for a turnkey solution. For Amazon, we have a AWS Marketplace product that you can click on and just seamlessly installs the server on your machine. Marketplace is kind of like the app store for server apps in Amazon. And when that's installed, the server auto-configures based on the type of instance it's installed to, connects with AWS CloudWatch for monitoring, and we provide support for the system. Okay, so a little more about H5PyD. So we mentioned H5Py already. H5PyD provides this compatible H5Py, and it's a pure Python that uses HTTP talk. It's asynchronous. So it's, actually I mistake that. It actually is synchronous, but it's taking these Python calls and using the request package to talk to the server. And there's a few extensions to H5Py. You can list content in folders. You can get and set ACLs, which are a way to control permissions to files on server. And there's a PyTables-like extension to the dataset. So I think it was some discussion in the H5Py community of merging PyTables and H5Py, and that's been a little more challenging than we may have thought originally, but it was quite a bit easier to do within the context of H5PyD. So for example, in H5PyD, you can have a data set and do a query on that and select rows of the data set that meet a certain specification. And the REST file, like I described, it's plug in to HA5, your public API stays the same, and you're converting these calls into REST requests. And I should mention that in the REST file, it's this high level. So, one challenge is if you took an H5 API call, like say create dataset, and that became many REST requests, that would introduce latency. But typically, one API call is either one or less than one HTTP request, right? So to create a data set in HA5 APIs, it's several steps, right? You define the data type, you define the data space, then you create the data set. All those interactions are happening within the vol. And it's finally when you create the data set, it's making the HTTP request. So in the context of the REST API, it's just one request to create a data set, and that request is providing all information, all the context in terms of the data space and data types, chunking, and so on. So command line tools, we have our hsinfo to display server stats, hsls as contents, hsmove to move a file, hstouch, create a file, hsdelete or rm to delete a file, hsload to upload a file, hsget to download a file, and hsackle. Again, these are all implemented using H5PyD. Okay, so this work has been going on for a few years, and I just want to touch base on some recent new features we've added. So, one downside of this new schema is that you have to I just say transmogrify all the data of your HDF file. So if you have like a large collection of big files, that's rather expensive. And if these files are already being stored, say on S3, now you've duplicated all that storage. And that's costly, if nothing else. So we instead now support this ability to just convert the metadata of the HDF file to the HSDS schema and leave the chunk data where it is in the file. And now when you read that data, it kind of remaps those to S3 range gets to pull the data from the original source file. And typically, the metadata for an HDF file is less than 1% of the overall size of the file. So here on the right, we have our HDF file that we've pushed up to S3. On the left, we have the metadata that's been imported to HSDS. And if you're doing things like reading links or getting dataset types or space, it works just like before, except when you're reading dataset data, it figures out which chunks are being accessed, and it transparently redirects those to S3 range gets on the original source file. Okay. So using this setup, it's much faster to import files, and you're not duplicating the storage cost. Okay, I don't want to steal Jean-François' thunder, but we're working with OpenIO, and this idea here is to have an OpenIO storage cluster that's also an HSDS server. So you have one cluster now, not two, and you have the scalability on multiple machines, and you have ease of maintenance because there's only one thing to maintain. Okay, next. So I talked about containers and how with HSDS you can have more containers, but at some point there'll be only so much CPU and memory on that machine to run your containers. So you'd like to run these containers across multiple machines. And Kubernetes is a system that lets you do that. So in Kubernetes, you say, Kubernetes, I have this container, please find a machine to run on. So you have this Kubernetes cluster of your machines, and the containers don't care which machine they are on. And this lets you scale up the number of containers to a much greater capacity than you could with a single machine. And more containers means both that you can handle more clients simultaneously, and individual clients get more parallelism. So remember, when you are doing a selection across chunks, say you cross 100 chunks, if you have 100 containers to run the server, each of those containers can be processing one request rather than say 10 or 50 requests. And so those requests get handled faster. A nice thing about Kubernetes is that you can add more machines dynamically to the cluster, and you don't need to interrupt the service, right? It'll just have more capacity to run more containers. And the other nice thing is, people who are worried about either cloud vendor lock-in are thinking they want to develop code on-prem, but with this later maybe to migrate to the cloud. With Kubernetes, you have the same API and the same kind of management tool set, and that works, on-prem or with AWS or Google or Azure. You have this common interface. Speaking of metadata access, so I observed, some conventions for storing HDF files create a lot of groups and metadata. And in the server, each time the client needs to talk to a server, there's that latency, right? Because you're going off the machine to a server and back again. And if you're doing, let's say, lots of attribute reads in different groups, all that latency can add up. So we did this feature where you can import, at least for read operations, you can import all the metadata for a file in one request. and then that metadata can stay on the client. And then future requests, like getting links for a group or read an attribute, occur almost instantaneously because it's all on the client. It doesn't need a server round trip. Okay, so next, I want to talk about a customer we worked with rather closely called NREL, the National Renewable Energy Laboratory. And despite Donald Trump being president for almost 3 years now, we still have a renewable energy laboratory, so that's great. So NREL has a problem in that they had 50 terabytes of simulation data they created on HPC system. They've moved this to AWS, but they wanted to share this with the broader public. And it's not very convenient, for individuals to download 50 terabytes of data to get access to this. So HSDS turned out to be a great solution for them. Their data is basically it's a 3D data cube. You have 2 dimensions for the latitude and longitude, and 1 dimension for time. And the time span was like 7 years, and the frequency I think was 30 minutes or 5 minutes. I forgot. So if you ever tried copying 50 terabytes across the public internet, it doesn't work very well. They use this device from Amazon called Snowball, and basically like it's a briefcase, and you attach it up to your local servers, and then you put it on a UPS truck, and it goes off to an Amazon data center where they unload the data to S3. So in this case, they had 84 HDF files, each about 500 gigabytes, 40 data sets per file, 1 month of data per file. And when we converted it to HSDS, we didn't convert that as 84 HSDS files. We created 1 HSDS domain or file that was the amalgamation of all those source files. So if you are, an application programmer, it's much more convenient to work within this context of 1 file rather than thinking, okay, I need to, get this chunk of data, but that's on a different file, and I have to open that file and get that. By having this 1, large file, it makes it much easier for people to access the data. This would be a problem in the POSIX world, right? Because your sysadmin may complain, if you have a 50 terabyte file to back up, or you may not have a file system that supports that large an extent. But within the context of HSDS, it's not an issue because remember there's no single object that's larger than a few megabytes. And so in this collection, we have 27 million objects, but to the application user, they only see this 1 file, right? They're not aware of those millions of chunk objects floating around in the storage system. So with this, we can do things like take a data set. This is a Python syntax where you say, okay, I want time step X and all the data from the lat long values. And this request, do some math here, it's accessing 288 chunks. Okay, so each of those chunks needs to be read from the storage system, uncompressed, and the data we want segmented out of that. The more data nodes we have, the faster that process will go. It's reading 403 megabytes of S3 data, and only 18 megabytes is returned, right? So this is really handy, say if I'm outside of AWS or outside that region, because I only need to read 18 megabytes. But the traffic between this S3 storage system and HSDS is 400 megabytes. So since that is all within the region, that transfer happens fairly fast, and there's no egress charge for that data transfer. In Amazon, if you're moving data out of the region, there's a cost of 10 cents per gigabyte, I believe. So here, you're speeding it up because most of the data movement happens within the region, and you're reducing the cost of access. Even more challenging is when we go the other way. So imagine you have this data cube, and now rather than slicing like this, I'm going to probe it like that. Oftentimes in HDF5, data sets are created with a certain chunk layout that say may be convenient for the producer of that data. And now they give that to users, and the access pattern for reading may be different than the access pattern for writing. And if your access pattern is, so to speak, cutting across the grain, that performance can be very slow with the HDF5 library, because in the HDF5 library, every time you're reading a chunk, that's a sequential operation, right? You're reading that part of the file, pulling the memory, uncompressing it, segmenting it, and so on. So here we have 3.4 gigabytes of S3 data being read, and only 240 kilobytes of data being returned. So there's a massive amount of data that has to be read to extract a single time series. So conclusion, we've been running with this data set for more than a year. It's available for public use. We have hundreds of users, millions of requests. The service has run pretty much faultlessly, low maintenance. The cost has been fairly moderate. One server, 50 terabytes S3 storage. And NREL seems to be pretty happy with it, and they're expanding the use of HSDS to incorporate more data sets. So this, they have a data set called the National Solar Reflections Database. It's currently only on-prem, and they want to, again, export it to AWS and make that available through the service. All right, okay, now let me shift gears a little bit and talk about Jupyter and HDF server. How many of you have used Jupyter notebooks? Good. And how many have used Jupyter Hub? Slightly less, right? So the nice thing about Jupyter is that this is interactive Python environment, and it's very good for data exploration, visualization, and such. The nice thing about Jupyter Hub is that you can access a remote server. So if your data is on the cloud, rather than copying all the data locally, I can just have the interaction between my notebook and the data happen in the cloud, and I only see the results. I only see the plots and such. So with Jupyter Hub, we have these notebooks. With Jupyter Lab, it's a new generation of the notebook interface. I think they just released the version 1.0. One thing I like, it has a terminal window, right? So I still want to do my terminal stuff. And you can use Kubernetes, again, as a way to manage the containers, both for Jupyter Hub and for user sessions in Jupyter. And that looks like this. So here we have a data center. Running that is Kubernetes. So Kubernetes is running across a cluster of servers. And Kubernetes can support these heterogeneous workloads, right? Different types of containers. You have Jupyter Hub containers, you have the HSDS containers, you may have other application-based containers, and they all can run within this context of Kubernetes. Let me do mine. So we have user. So user connects through Jupyter Hub. And in our implementation, we're using this Auth0 client, which manages our HDF group sign-in portal. Once you've authenticated, you spawn a new container. So here's my container. And that container has a local disk volume that you use for traditional POSIX files and such. Okay, so far this is all pretty much like any other Jupyter Hub installation. But what we've done with this thing called Jupyter Lab is that your container is automatically connected to a HSDS server, and that can store data in an object storage system. So now you can have files that are much larger than could be stored on your local disk, and you benefit from the parallelization of HSDS, and also it makes it easier to share files. So in Jupyter Hub, if I have a file here, and say Mike is running this container, and I want to share this file, there's no direct way I can do that. I would have to, you know, download it and then send it to him through email or something like that. Here, I can create a file on HSDS. I can modify permissions, so Mike has read permission for it, and I can say, send him a pointer to that file. And now he can access the same data I have, and we're not duplicating the same content over and over again to make it accessible. Okay, there's some effort to build in more collaboration with Jupyter Hub. Currently, it's pretty much you're storing your notebooks in GitHub or something, and then you have to copy that. But current work is to make it more of a collaborative environment like Google Docs, where you could have multiple users working on the same actual notebook. So here's what I was talking about, that you have any size collection on a server, you can share with anyone, and each user controls who has access to what data. There's also a fair number of data sets that we've put in to make shareable with everyone, like sample data sets to illustrate the use of HSDS. So this is available now. So go to hflab.hp.org and sign in, and you get your own Jupyter Hub environment. And you get, it has notebooks, tutorials, free data sets. There is a small fee of $10 a month after a 2-month trial period. And so if you are looking for a way to conveniently share files on the web, this is good. If you're looking to try out HSDS without having to install it yourself first, it's also a good thing to do. Okay. So I like this XKCD comment. So anyone has this environment on their notebook, you know, with the different Python versions and kind of. So nice thing about Jupyter Lab is that you have this kind of cohesive Python environment that you don't need to deal with. Features, so each user gets 1 CPU core, 8 gig RAM, 10 gig disk, and 100 gigabytes of S3 storage in HSDS. And we can configure that to more if you have special requirements. And a common set of Python packages. If you have some package that you'd like to see, just let us know, and the command line tools. Okay, and finally, these are some useful links, and that's it. So, so I was going to do a demo. Should we take questions first, or just go straight to that?
Questions?
Yeah, question about the container orchestration. Have you estimated how much overhead you get by using Kubernetes that is deploying Docker containers instead of having more instances of objects?
Right. Yeah. Yeah. So there will be. Let me go back here. So when you're running on a single machine, when all these containers in a single machine, then the one container talking to another container is very fast. If these containers are distributed across a Kubernetes cluster, then obviously there'll be more latency. But the benefit is that you can get more parallelization. So I think your mileage may vary. It kind of depends upon the application and how large the server is versus how many servers you have on a Kubernetes cluster, and so on.
Other questions, sir?
Yeah.
How dynamic is that architecture when you add more if you want to scale up?
Right. Yeah. Yeah. I meant to talk about that. So in what we don't have yet is this idea of auto scaling, right? So to reduce costs, right, you may prefer to run with the minimal set of containers to meet the current load. But then when load comes up, you'd like to install run more containers. And if you could actually run more machines in your cluster at the same time, that would also be good. So currently, we can only do this manually, right? So the future work would be to have this logic say, oh, there's more load coming in, fire up more machines, run more containers, process that workload, and then when the workload goes down, reduce those resources. The server has this limit that's configured for how many in-flight requests each node can handle. And I think it's set to like 40 requests simultaneously. If there's more than that many requests, then the server says, hey, I'm booked, you get 503 response. And that's a signal for the client to kind of back off the workload. It's very challenging, in the scientific computing environment because the workloads are very dynamic. If you're serving YouTube videos, you kind of know how many users at any point in day will be watching videos, and you can kind of scale your resources appropriately. In the scientific computing world, you may have nothing going on, and then I fire up a Spark cluster that's going to be bombarding a service with thousands of requests. So we have to be able to scale to meet that load.
Another question? I had one which was, you said you could leave the raw data, or the chunks you could leave in traditional file storage, POSIX, and then just transfer the metadata. Is this something that you can then imagine you can still access the file from POSIX as well as from HSDS? Because we have lots of data which is in POSIX. You could imagine making it available. We'd like to make it available remotely.
Right.
Would we just leave it there that people might do either POSIX or HSDS?
Right. Yeah, that's it's not a feature we've implemented yet. I don't think it would be hard to do. In the public cloud world, POSIX data is much more expensive than S3 data. So that's the kind of common way you have this data copied as you have your traditional HDF files copied to an S3 bucket, and then you set up HSDS to look into that bucket. For an on-prem world, it's very common to have a SAN or something where you have regular POSIX files and just need a little bit tweaked to do the POSIX call to get that. So I talked about Jupyter Notebooks and NREL. So here's how it all works. So we have a sample notebook on our Jupyter Lab instance. And I'm going to import the HID package. We have the right version. I mentioned the command line tools. So one is this hsinfo. And I can see that my server state is ready, which is good. This is the endpoint of the server. This is my username that I've logged in as my home folder. So each Jupyter Lab user gets a home folder on the server that they can use to create new folders or files. Node count's 8, meaning we have 8 data nodes, 8 service nodes. Right? And so that's about ours, and my HID version is 0.4.4. So another tool is HSLS, the equivalent of the POSIX LS command. And here I'm going to do this optional parameter bucket. So this is not a bucket we own, it's a bucket owned by the NREL organization. And I can see that there are a bunch of files here. The WTK-US.5 file is the one we'll be using here. And now I'm going to open this file. So if you're familiar with H5Py, it looks pretty much the same as using H5Py on with local files. One slight difference is that the ID in H5Py, this ID would be a numeric value. Here is a UUID string. And I mentioned how we can pull in all the metadata for a file in this file open call. So file open took 150 milliseconds. And now I'm going to read an attribute from the root group of the file. And that takes just 124 microseconds because it's already gotten cached on my client. So think about it, you have a 50 terabyte file. I can pull off this attribute, very minimal amount of overhead. And oftentimes you're doing types of analysis that don't require the dataset data, and it's all very efficient. So let's list all the data sets. There's a bunch of data sets. We'll grab one data set. Again, it has a UID. The shape is 613681602 by 2976. So it's three-dimensional data field. And it's port 32. We have a chunk layout of 24, 89, 186. And if I multiply these dimensions, it turns out that each data set is around a terabyte. And we have 40-some data sets. So I'm going to read a slice off this data set. So here, we obviously don't have this data cached. We have to go to the server to get it. And this came back in 700 milliseconds. And I can do a plot. So voila. We have, it kind of looks like the Continental US, but it's actually colored by wind speed rather than anything else. There's a little bit of cheating going on here because this data set likely was in memory on the server when I did this. In Metadata library, there's this chunk cache, which I think is the default 2 megabyte cache. On the server, the chunk cache can be gigabytes in size. So any data that's recently been read can live in that server memory, and any client that reads that same data gets the cache value and doesn't need to go back to S3 and compress the data. So I can rectify this by changing this value. Let's change it to 623. And now it'll take a bit longer. So 3.64 seconds. And then if we run it again it's fast. And if someone else came and read the same file and got the same data set, they would get these cache values. And I can actually change, let's say, 2 by 1, and this also should be fast. Because it's caching not the result of the request, it's caching all the chunks that are read for the request. Okay. Now, so I mentioned going the other way, orthogonally, it's more intensive because you're going through more chunks. So this call will take a little bit longer. So 2.8 seconds, and we read this time series of 7 years of data. And we'll plot that. And voila. So this is kind of a flavor of what we've done. Let me show you. Anyway, I want to show a Nexus file, because I know we have some Nexus. So you can say HSInfo and file name, and you get information like the total size, total number of bytes, number of objects, number of chunks. You can list the contents of the file. So Nexus has a very deep hierarchy. And then opening the file took 300 some milliseconds. And again, when we access attributes or metadata file, it's very fast because it's not going to the server. Right. Cool. So that's it for the demo. So conclusion, I think this is a very interesting technology. I can say it myself. And I think it may not be suitable for everything, but it's certain utility to make sense.
questions?
Is the notebook you've got open here, is that available for us to view ourselves, to work on set projects and we can play around with it ourselves?
Yes.
Fantastic, thank you.
Yeah. So when you first log on to QLab, you'll see this folder called HDF examples, or HDF lab examples, and it has this actual Python notebook.
So in your presentation, you said that file access you chose is not compatible with the HDF library version. So I understood this for performance reasons and so on. The previous presentation talked about the performance problem. So is there any plan to merge the work you did with the HDF library?
Are you talking about the wall itself or the server? No.
It was about accessing the way you access the HDF file, which is not compatible with the HDF, the current version of the library. So, do you think there is a plan to merge this kind of the way you access it with the HDF library?
Well, I mean, you can use the RESTful with HDF library to access it, and then you have a C application that is going into the HDF library, invoking the RESTful. RESTful makes HTTP requests to the server and back again. Is that what you're referring to?
For me, it was more what you did inside this RESTful library.
Mm-hmm.
Is there no way it can come up to the classical library?
I think it's based pretty much on this object storage and schema. I think it would be interesting to have a HDF library implementation that directly read and wrote to an object storage system. So it could be like an underball that's not going through a server, but it's directly accessing the object storage system. But that's work that we haven't started.
Thank you.